In this section, we will explore how factory production and quality control shape the success of modular construction. One of the most important differences between modular construction and traditional site-built construction is where the work takes place. In modular construction, many building activities move from the open job site into a controlled factory environment. This shift can create major advantages. It can shorten project schedules, improve quality, reduce weather-related delays, and make construction work safer. However, these benefits do not happen automatically. A modular factory should not be managed simply as a job site moved indoors. It must be managed as a true production system. That means construction managers need to understand workflow, station sequencing, material movement, inspection points, labor balance, and factory capacity. In this section, we will look at how modules are produced in the factory, how quality control is built into the production process, how lean thinking improves productivity, and what problems can disrupt factory-based construction. Factory-based construction treats the building more like an engineered product than a one-time field assembly. In a modular factory, materials, workers, equipment, and inspections are organized around a planned production system. Modules move through main stations, while substations, feeder areas, and storage areas support the overall flow. The main stations are where major work takes place, such as framing, MEP rough-in, drywall, interior finishes, and exterior work. Substations may produce smaller assemblies, such as wall panels, bathroom pods, cabinets, or MEP racks. Feeder areas make sure the right materials arrive at the right station at the right time. Another important difference is the construction sequence. Traditional site-built construction usually moves from the outside in. The structure is built first, the building is enclosed, and then interior systems and finishes are installed. Volumetric modular construction often works from the inside out. The process may begin with the floor chassis, then walls and ceiling assemblies are added, followed by MEP systems, insulation, drywall, paint, flooring, and other interior work before exterior sheathing is completed. This creates better access for workers and reduces congestion among trades. Factories may use either linear production or static production. Linear production is useful for repeated modules, such as hotel rooms, apartments, or student housing, where units move through workstations at a planned pace, often called takt time. Static production is better for complex or customized modules such as healthcare or laboratory units. In this approach, the module stays in one location and workers, tools, and materials move to the module. The key point is that factory production depends on protecting flow. If information, materials, labor, or inspections are not ready at the right time, the entire system can slow down. One of the strongest advantages of modular construction is the opportunity for better quality control. In traditional construction, quality can be affected by weather, mud, poor lighting, temperature changes, moisture, and site congestion. In a factory, conditions are more stable. Workers have better lighting, better access, and more consistent work procedures. But quality control in modular construction should not be treated as a final search for defects. It should be built directly into the production workflow. A key practice is the use of hold points. A hold point is a planned inspection step before the module moves to the next stage. For example, before drywall is installed, the factory may check framing, fire blocking, MEP rough-ins, fasteners, and system connections. This allows problems to be corrected while the work is still visible and accessible. Another important practice is third-party certification. In many modular projects, state-approved inspection agencies review electrical, plumbing, structural, fire protection, and other systems during production. Once the module passes the required inspections, it can receive a certification label before shipment. The local authority still reviews site-built work, foundation conditions, intermodule connections, and final installation, but much of the module itself has already been inspected in the factory. Advanced factories may also use 3D metrology, such as laser scanning. A completed frame can be scanned and compared with the BIM model to verify dimensional accuracy. If a module is out of tolerance, it can be corrected in the factory, where tools, access, and inspection support are available. That is far less expensive than trying to fix the problem during crane setting on site. Lean thinking is highly relevant to modular factory production because the goal is to reduce waste and increase value. Lean manufacturing is often associated with the Toyota production system. In modular construction, lean thinking helps managers organize workstations, control material flow, improve labor flexibility, and take advantage of repetition. One important lean method is value stream mapping, or VSM. This helps managers understand how materials and information move through the factory. By mapping the process, managers can identify bottlenecks, unnecessary movement, waiting time, and other forms of waste. Another method is 5S, which stands for sort, set in order, shine, standardize, and sustain. In practical terms, 5S means that tools, materials, fasteners, and equipment are organized so workers do not waste time searching for what they need. Just-in-time delivery is also important. Modular factories need a steady supply of materials, but too much inventory can crowd the production floor. Electronic Kanban systems can help signal when parts should be replenished so materials arrive at the correct station when they are needed. Cross-training also supports production flow. When workers are trained to perform more than one task, they can help at another station if that station falls behind. This flexibility helps keep the line moving. Finally, modular factories benefit from the learning curve. When workers produce similar modules repeatedly, they become faster and more consistent. On high-volume projects, production time per module can decrease significantly as the team gains experience. The main lesson is that lean thinking turns the factory into a continuous improvement system, not just a place where construction happens indoors. Although factory production offers major benefits, it also creates its own management challenges. The first major problem is bottlenecks. A bottleneck occurs when one station takes longer than the others and slows the entire line. In linear production, the production line can only move as fast as its slowest station. If mechanical installation takes much longer than drywall installation, downstream workers may be forced to wait. Managers need to balance cycle times, shift work to parallel substations, or add trained workers to the constraint point. The second challenge is wet trades. Many factories reduce this problem by using dry alternatives, such as pre-cured panels, structural insulated panels, or prefabricated floor systems. A third challenge is supply chain gaps. A modular factory is highly sensitive to missing materials. On a traditional job site, crews may be able to shift to another task if one item is delayed. In a factory, one missing window, fixture, or specialty component can stop the line. For this reason, procurement planning, reliable suppliers, and buffer inventory for critical items are essential. The fourth challenge is late design changes and over-customization. Factory efficiency depends on repetition and stable work procedures. When design changes occur after production begins, they may require revised drawings, new material orders, updated fabrication instructions, and retraining at the workstation level. This is why modular projects need design freeze and controlled variation. The factory should protect repeated chassis layouts, MEP routing, and standard work sequences, while allowing limited visible variation when it does not disrupt production flow. This case study shows how inspection checkpoints can reduce rework in modular production. Mesocor, a volumetric modular manufacturer in West Palm Beach, Florida, organizes production as a manufacturing process rather than a traditional field construction sequence. Instead of waiting until the end to find defects, the company embeds inspection directly into the production line. One important practice is the use of embedded checkpoints. MEP systems are inspected at each stage before walls are closed. This means that defects can be found near the station where they occur, while the work is still visible and easy to correct. Mesocore also uses third-party certification. Intertek reviews key systems including MEP routing, electrical panels, and plumbing pressure before drywall is installed. This connects quality control directly to the production workflow. The result is a high first-time quality rate. According to the slide, Mesocore has achieved 91% first-time quality, meaning that only a small portion of the work requires correction. This is important because rework in construction is expensive. In field construction, a hidden problem may require demolition, correction, and rebuilding. In a modular factory, the goal is to catch defects before the module is sealed, shipped, or installed. The broader lesson is clear. Factory production creates value when quality control is proactive, structured, and built into the production process. For construction managers, the goal is not only to produce modules quickly, but to produce them correctly the first time.